So we have technically looked at a bunch of power series, and I think I briefly mentioned that Taylor series can all be written as a power series, but we also have other types of power series besides just our Taylor series. Which is why last week we looked at a little bit of things that we could manipulate in order to get us different types of power series. We also looked at integrating to help us get power series on Friday. And today we showed the last little bit. You don't have to write all this down. Basically, just notice that the convergent form of a power series, yes, is that I have an a sub n times x minus c to the n power. And then our definition of a Taylor and Maclaurin series, okay, is very, very similar. So, and basically it's just us writing, like this right half should look real familiar, because that is our definition of a Taylor polynomial. It's just rewriting it now in series notation. Yes? No? Maybe? Okay. So this is find the Maclaurin series in summation form for the following instructions. Find the interval of convergence for each series as well. So we've already, technically we could get away with manipulating this if we wanted to, but we're going to go ahead and do this from scratch, like if it was just some other Maclaurin series, just so we can kind of see the process of what would happen if we wanted to write it out based upon our Maclaurin or Taylor polynomial instead. So what do we need in order to write out a Maclaurin polynomial? We have a function. Yeah, we need derivatives, right? Because remember we plug in our center, which if it's a Maclaurin means it's centered at 0, so I need stuff to plug 0 into, okay? And because it does not technically tell us how many we need, right? There's not actually a set number. I would say we usually want to start with like 3-ish, okay? Because at the end of the day, it's asking it for in summation form, which means that I just need to be able to see the pattern so that I can write it out in its general form. Does that make sense? I would say with just 2 derivatives, you might not be able to see it, so I'm usually going up to 3. If you can't see it just from that, that's maybe when you would add in more if needed. Are we all with me there? Alright. What's our first derivative going to be? We can technically rewrite this as cool. Remember, we're subtracting 1, right? Because it's derivative. So we would get. Yeah, we bring down our -1, but then remember, I'm also going to have to do a chain rule, so then I would also be multiplying by a -1. So it's going to end up being positive. Agreed? And then I would have 1 divided by 1 minus x to the second. Are we okay with that? So then what would our second derivative be? This time we would bring down our -2, yes? But then again, we would be multiplying by a -1, so the negative is going to go away, but I'm still going to have a 2 there? Yeah. Okay, and I said we were going to go up to 3, just to kind of give us enough. But what are we going to get on that one? 6. Cool. Are we all okay with that? Then what do I need to do with each of those? Plug in 0. So what do I get for f of 0? Okay. What do I get 1. What do I get for f double prime of 0? What do I get for f triple prime of 0? Notice that if we took another one, what would I get there? Like what number? 24. What numbers do those look like? Factorials. Okay. So we want to start looking for our patterns as early as possible, if we can. Okay. So it looks like that our f to the n of 0 is just whatever our n factorial is. Yes, no, maybe so. Okay, so then our f of x would equal, so what's our constant term up front? 1 plus, my first derivative was just 1 times x minus 1, x minus 0 to the first power, so we're just going to get x, cool, plus what happens to my 2's? They're going to reduce, right? Because my derivative is going to be divided by my 2 factorial x squared plus, my derivative is 6 divided by 3 factorial times x cubed. Yes? So in general, notice, going from I would have, on top is usually our derivative, right? But we said in general form our derivative is n factorial divided by another n factorial times x to the n. So what happens to our n factorials? They reduce. So we just end up with an x to the n. That's a bad n plus dot dot dot. Decimal maybe? Are we okay with that? So this is kind of the long way if for some reason we could not figure it out. Would there have been a shorter way to do that?
Yes.
What is 1 divided by 1 minus x? It's the sum of a geometric, yes? And the sum of the geometric is, remember my formula is a times x to the, r to the n power? Yes, where a is what's on top, so that happens to be 1. And our r is whatever's being subtracted here, which happens to be x. So we could also get it that way. But again, this was also good practice for us to see like how we might build this out if it wasn't in one of our nice pretty forms. But I will say a lot of our things that we have are going to be in a form where it's easy for us to either rewrite it as a geometric, which is like what we did last week, or where we could take the derivative or take the integral of a easier power series, kind of like we did last week. Yes, no, maybe? So then the last part that it asked us to do is to find the interval for of the convergence. Yes? What's our interval of convergence for geometric? What's our r here? Has to be less than 1. So what do I get for my interval? So 1. And remember with our power series, because we end up, with our power series and geometric series, I can't plug in the 1s because it gives us zeros in bad places, so we're not going to have to worry about our endpoints. So this would be my interval. Questions on that? Yeah. Alright, next up, this is just a reminder of the 3 that we need to have.
I have
Universe? Sure, what's up?
Where finding like the bound?
Here?
Yeah.
So remember, we talked about how this is a geometric, yes?
Mm-hmm.
And remember that in order for a geometric series to be convergent, r has to be less than 1.
Mm.
And then remember that my sum for a geometric is a divided by 1 minus r. And so in this form, a is my 1, and then r is my x. So if r has to be, absolute value of r has to be less than 1, my x is in the place of my r. So in order for it to be convergent, which is what it's asking for the interval of convergence, I know that x has to be less than 1.
Okay.
Which is why we like it when we can write things as geometric, because we can just use this format and we don't have to do the ratio test. Which isn't necessarily hard, it's just longer. Other questions?
So you're saying that the sum equals, because we're putting it into, we would have been putting it into summation notation, f of x equals the sum, and so you're able to say that that is the sum of the whole thing because it is f of x?
Correct. Because the sum of a geometric equals a divided by 1 minus r, right? Which is what that is. So f of x is a geometric sum, which means that in the summation notation, this is a geometric series that equals f of x, because f of x is the sum of all of your series. Which is why it does have to be infinite, because if I were to cut that off at any point, it would not equal f of x. It would just be an approximation for it. The other question? So I think these are the three that we talked about that have the little hearts next to them. The other one that sometimes comes up is, so the 1 divided by 1 plus x is what we did on Friday, I believe. So remember that was where our r is going to be negative x, so it's going to be very similar to a geometric, which we get x to the n. The only difference is because I end up with a negative x here as my r, it's an alternating, so I get negative 1 to the nth power. So those are just the ones that are good to know, because they help us from having to derive stuff. The other ones you'll see from time to time, but not quite as often. Alright, we're going to look at an FRQ real quick. We're going to put it all together. I think we had questions about is a series test, or is a series question going to be on the AP test? The answer is yes. And yes, it is usually one of your free response questions. So, this says the function has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 equals 1, f prime of 1 equals negative 1/2, and the nth derivative of f at x equals 1 is given by f to the n of 1 equals negative 1 to the n times n minus 1 factorial divided by 2 to the n for all n is greater than or equal to 2. So on that first part, on part A, it asks us to write the first 4 non-zero terms of the general term for the Taylor series, which is technically asking us to find a Taylor polynomial with 4 terms. Okay. So what are we going to need there? So I have f of x is going to equal, so the first one is just going to be f of 1, right? Because we're centered at 1 this time. What is f of 1? 1. Okay. And then I would have f prime of 1. Yes, which is what? Negative 1/2 times x minus 1 to the first power. So far, so good. Plus, what do we need here then? Yeah, I need my second derivative, yes? So notice that it gives us the equation to find our derivatives instead of giving us actually the original function. So if I'm looking for my second derivative of 1, so n is acting as our number of derivative. So what's my number of derivative here? 2. So I have negative 1 squared times 2 minus 1 factorial divided by 2 squared. Yeah? Do y'all see where I'm getting that from?
Yes.
Alright, so negative 1 squared is just going to be positive 1. 2 minus 1 is also 1. 1 factorial is also 1. So I just end up with a 1/4. So I have a 1/4. What's also going to be in the bottom of that? 2 factorial. Which is, yes, 2. Times what? How many more terms do I need? Just 1, right? Because it doesn't say, so like the 4th derivative, right? It just asks us for 4 terms. So since I didn't have a 0 as my first term, I only need to go up to my 3rd derivative. What is my 3rd derivative now going to be? We'll have a negative 1 to the 3rd, so that's going to make it negative. Going to have 3 minus 1 factorial divided by 2 to the 3rd. That's a 1 there. So what do we get there? So this would be like 2 factorial over negative, right? 2 cubed? Guess the way. So plus. And the reason why I leave it like that, what might that help us do then? Because what does part A ask us for? Ask for the first 4 terms, but then also the general term, right? So leaving it in factorials and or 2 to the stuff helps us better see what that pattern is. Are we all with me there? And it's also not wrong, remember, to leave stuff as long as it's numerical values. We can leave it like that. We don't have to find the actual I. So we have minus, we have a 2 factorial on top and a 2 to the 3rd with a 3 factorial on bottom times x minus 1 to the 3rd power. So those are our first 4 terms. Now what do we need to find? The general term. Okay. Easiest first part is what's happening for my signs. They're alternating, and we start positive, and then go negative, positive. But remind me, what does our n start at? 0. So we'll have negative 1 to the just the n. So even though it's our second term, n is technically only 1 for that second one. Yes? So this is why we get negative 1 to the n. Then what do we have on top? I think it's easiest to probably see from our 3rd one. I have a 2 factorial on top, yes? Yeah. And 2 factorial, how is that related to my n equals 3?
N minus 1.
N minus 1 factorial. Okay. Then I have a 2 to the 3rd, or in this case we had a 2 squared, so that's going to be 2 to the n. And then I also have a 2 factorial and a 3 factorial on bottom. What are those going to be?
Yeah.
Just an n factorial. Times our x Robert must have adjusted. We need to reduce some anyway. Because notice that we have factorials on top and bottom, right? And we're going to reduce those. How would I reduce those though? Can I? Okay. So we're used to looking at something that is n plus 1 factorial equaling n plus 1 times n factorial, yes? So I subtract 1 to get the factorial part, yeah? This time I'm starting with an n minus 1 factorial. So I actually don't want to rewrite that because you would have n minus 1 factorial times n minus 2 factorial. Or sorry, n minus 1 times n minus 2 factorial. That is not super helpful, yeah? But notice on the bottom, if I go back 1, what would I get from that? N times n minus 1 factorial. Which is why that's actually the one that we want to write. Or rewrite. Because then if I do that, my n minus 1 factorials would reduce, and I'm just left with a 2 to the n times what? N? And then I still have my x minus 1 to the n out. Which then takes care of our problem. Yeah, we don't want negatives in it.
Can we take factorials as negatives?
I don't think so. The only way to do it would be to rewrite it so that you're factoring out your negative. And you don't really want to do that, so easier just to simplify. Alright, so we did both parts for part A, yes? We found the first forward non-zero terms, and then we found the general term. Agreed? Yeah.
Did you have to simplify to get the general term? Could we just have nothing?
Could we just have left it? I would have to look at the point breakdown. I've never graded BC topics, so my gut is to say no. The only time that it would be necessary is if it created problems, like you were talking about. And so what I need to make sure is that if that -1 being in a factorial would be considered a problem. So I'll look it up and get back to you. This is from 2016, so I can look up the score breakdown. Alright, on the next one, it says the Taylor series for f about x equals 1 has a radius of convergence of 2. Find the interval of convergence. So what has to be in the middle? So what value has to, I should rephrase that. What value has to be in the middle of our convergence interval?
Is it 1?
1, right? It has to be your center. Are we with me there? The other way that we can think about that is that if I am not centered at 0, then technically x minus 1 is what would go on the inside from 2 to -2. Because my radius, my r is 2. So we get that x has to be in between -1 and 3. Agreed? But this was not a geometric series, yes? So what do we have to test?
Intervals.
Our endpoints. Which is, this is where it would probably be more helpful to have it simplified because I'm going to have to plug those values in. And so it's going to be a little bit easier to see if it's convergent or not when I plug those values in. Alright, what do we want to plug in first? -1, sounds good. So I have a -1 to the n divided by 2 to the n times n. Now times -1 minus 1 gives us -2 to the n. Yes? But do we usually put, or what do we usually do with that negative? Turn it into an alternating, right? So I would have another -1 to the n, but if I have -1 to the n times -1 to the n, what is that technically? -1 to the 2n, which means what's always going to happen?
It'll always be positive.
It'll always be positive. So if I have 2 -1s to the n, right, or an even amount of them, they basically reduce each other out then. So we no longer have an alternating. Yes? So then the other thing is, once I pull that negative out, I have a 2 to the n divided by a 2 to the n. What is that? They reduce, and I'm just left with 1 over n. What does 1 over n do?
Diverge.
Diverges. So am I going to have an equal to bar on -1?
No.
No. Okay. So then I have to check 3. What is 3 minus 1? 2. Yes? So what happens to my 2 to the n's again? They reduce. So this time I'm left with that alternating series still. And what is that? Huh? It's an alternating series, right? But is that going to be convergent or divergent? It'll be convergent, right? So remember, like, that's kind of like our go-to conditionally convergent, right? Because it's convergent when it's an alternating. It is not convergent when I take the absolute values and just get our harmonic. So I would add an equal to bar for R3. Oscillate. Yep.
I don't think I understand when we have to check endpoints.
Basically, we don't have a geometric. Because we don't know if it converges or diverges on our.
Is geometric always?
So notice that, like, the easiest one was like the last one we did, right? So my sum is 1 divided by 1 minus x, right? My endpoints, we were centered at 0, but it would always work out this way even if you weren't centered at 0. One of my endpoints are the absolute value has to be less than 1, right? So if 1's my endpoint, if I plug in 1 for that x, what do I get? 1 minus 1 on bottom, which is 0. So it's not going to be allowed to be the endpoint. So because of that fraction that is created for our sum, for our geometric, it can't be your endpoint. Does that make sense? And that'll always be the case. Even when we're not centered right, it's now like x minus 1 or whatever, so then that moves it to 2. So then when I do the subtraction, I'm still going to end up with 1 minus 1. You'll still get a 0 in the bottom. So like whenever we have geometric, it can't be your endpoints. Which is why we like the geometric, because then it's not as long. But otherwise, we just plug in and check. And this one was nice because we didn't even have to find the radius, right? If we had to find the radius, we would have had to do our ratio test. But in this case, they gave us the radius, which was nice. So then we only had to check the endpoints. Yes. Maybe other questions?
And then what does it mean when the endpoint varies? Does it mean that like that one's just like not right, like it's gonna be a different bound?
Sorry, say the first part again?
What does it mean? So like you know how we try -1 and it diverged?
Yes.
What does that mean?
That means that, say my x value, so like, again, this is like is an interval of x values that will make this Taylor series converge. So it's kind of think of it like a domain for my x, right? Which means that -1 is not included in my domain, but 3 is included in my domain. So when I plug in -1, I'm not going to get a convergent series. When I plug in 3, I will get a convergent series.
So anything greater than -1 would work?
Correct. Yeah. So I could plug in 0, 1.2, 1, 3, 4, right? That interval already gives me all the stuff in between, so I don't have to worry about the stuff in between, but I do have to worry about the ends when it's not a geometry. Yeah, does that make more sense? Okay. Alright, so we got C and D, but they're pretty fast. Same prompt, so you don't have to like rewrite that. But so it says the Taylor series about f, or for f about x equals 1 can represent f of 1.2 as an alternating series. Use the first three non-zero terms of the alternating series to approximate f of 1.2. Luckily, we already found that basically, yes? So what are we technically finding here? A Taylor polynomial, so p sub 2, yeah? So I'm just going to use the first three. So that was that 1 minus 1/2 times x minus 1 plus, what do we get? 1 divided by 4 times 2 factorial times x minus 1 squared. I'm just like rewriting from what we had on the last page. But I did not use the third one because it only asked us for 3 terms this time. Are you with me there? Now what are we trying to approximate? 1.2. So I'm just plugging in 1.2 to all of that. Agree? And we should get 0.905. Yeah.
Is it Taylor polynomial only whenever you're approximating? I don't think I know.
So technically, anytime that we cut off a Taylor series, it is a Taylor polynomial. So this was technically a Taylor polynomial because we cut it off.
So could we say P as upper box?
Yeah, this one we could have said p sub 3 and we would have been fine. Yeah.
Okay.
It's just this one also asked for the general term, so you did need to find that part as well. And so that's why they tend to, like, when they ask for a general term, we don't tend to write the general term with the Taylor polynomials. We tend to write the general term with the series. So, like, that's why we tend to use the f of x if it's asking for a general term versus, like you were saying, when we're doing approximations, we're never going to find a general term. So, like, it will always be p sub whatever when we're doing an approximation. But yeah, I mean, like, you can almost use them interchangeably, but, like, the only difference is that, like, your Taylor polynomial, it is an approximation, so it will have an endpoint, versus the series is what actually equals the function. Kind of like the difference between, like, a Riemann sum versus an actual integral, right? My Riemann sum is just an approximation, so I only have so many squares, whatever. But then the actual integral goes on forever because that is the actual area, versus my Taylor series is the actual function. My Taylor polynomial is just the approximation. Does that kind of make sense? And then, so that's my approximation. What is the last part asking us for?
Error.
The error. How do I find error? So I'm looking for my r sub 2, right? My remainder, you could also put e, right? Because no remainder, error, same thing. You could also put f of 1.2 minus p sub 2 of 1.2, because it's my function minus my actual, or sorry, my actual minus my approximation. And then what does that have to be less than or equal to? Yes and no. The nice thing about, what did it say that this is technically writing it as? So do I have to use my max notation? No, I can use my alternating series bound instead. Do you remember our alternating series? Remember, it's the next term. It's the next unused term, right?
Aren't they, like, very similar?
They are. The only difference is if it's not alternating, then I just have to think of the maximum of the polynomial, which, think about, they don't give us f. So I would have a hard time. You could look at the maximum of the next derivative, which would be f of n plus 1 plugging into that thing. That's also not going to be fun to try and find. So that's why it tells us that it's an alternating series, so we're going to use our alternating series bound. So that's just my next term, right? Oh, that's not maybe. Yes. Are we all okay with that? So because it's an absolute value, yes. So I'm just going back to our general term that we had here, right? I'm just plugging in my next term. So we went up to p sub 2. So my next unused term would be P3 or n equals 3, yeah. But because it's the absolute value, we really don't care about the -1 part. Agreed? So I'm just looking at 1 over 2 to the 3rd, yes, times 3, because it was just an n there. Again, remember, I'm just using that general term that we found for part A. I'm just plugging in 3 now instead. And then I would have 1.2 minus our center was 1, right? It's just going to give us 0.2 to the 3rd. And if you plug all that in, you get 1 over 3,000, which is less than 1 over what?